Welcome everybody. In this video we're going to do an overview of how computer RAM works. So what I've got here is something that I've already designed and built myself, which is sort of like an 8-bit register. So this is 1 byte of information this can store. Actually, let's get some lamps. Yeah, you can flick all these different inputs and nothing's actually going to happen at the output over here until there's a clock cycle. So more in the future, when we start to actually build a CPU, there's going to be a clock running to determine the flow of all the components in the computer. So each time the clock on the uptick, then the downtick, it's going to actually write the information into the memory. Now this 10101110, that's going to stay in here no matter what we do. Like, we can turn all the inputs off and nothing's actually gonna change here. It still is 10101110. Here, something I've been working on for a little bit. So I haven't actually redesigned the register or anything, so there's just 2 of them right here. But what we're doing now is basically figuring out a way to connect them all. So like, all of these yellow lines will be the input lines into this row of registers. There'd be more like behind it out there and to the side over here. So there'll just be one like big block. And these input lines, the signal will end up going all the way down this line. And you can see it goes up into that register and up into this register. And then we also have this output line, which will connect to that one and this register later. But you might be wondering, how is it that I only have one input line and one combined output line? Well, I'm gonna need to take you out of Minecraft to explain that. So to really understand what's going on, we have to break it down and see what these registers that I'm showing you actually are. So these registers are made up of these little components called data latches, which have 2 functions. They have the data in, so this is the input for the data. This will be either a 1 or a 0. And then we also have the write function. So the data will only be able to go into the latch if the write function is also on, or if the write function is a 1. And if we turn the data to 1, and it's not outputting anything yet, but then we turn the write enable wire on, it'll output a 1. If we go and untoggle the data wire and the write wire, we can send whatever information we want into the data port, but nothing will actually change the output. The output is still 1. And so basically for each of these registers, we have 8 of these blocks right here. So we just have like 8 of these little boxes side by side. And what we can do is we can give each of them a data input line, but then they can all share a write enable wire that goes all the way across. And then they also have an output. So that method of sharing wires is what we're also going to use later on with our array of registers. So with this one register, we saved ourselves some wires. Instead of having each of these with another write enable wire, we just have one that goes all the way across that we can toggle on or off. Here we have a 4x4 array of these 8-bit registers. Or we could also say that each of these boxes can store 1 byte of information. Now, we could have data input, and then a read enable, and then a write enable wire, as well as a data output wire for each of these separate boxes. But that would be way too many wires, way too complex, and there's no need for that. What we can do instead is arrange the wires into a sort of grid which overlaps across all of the different registers. We want to arrange this so that only when the row and the column wire are on, we'll get the register at the intersection of those two wires to activate. So in this case, it would be this register. Let's take a deeper look into what's actually going on at this intersection in this register. At the intersection between the two wires, we'll have an AND gate fed by the wires. This AND gate will only be on if both the horizontal and the vertical wires are on at that intersection that we have here. This signal will then be passed to two other AND gates with the write and read enable wires. This means that we can pass the write wire and the read wire to every single register in the grid, but it won't affect them, because if we pass the signal through an AND gate, it will only ever pass over to the register if we also have the signal from the first AND gate leading into it. And that will only ever be on at the intersection, the one that we can specify through a multiplexer, which we'll learn about later. So we can turn the write enable wire on, which will send a signal to every block in the grid, but it won't actually pass through to the register except for on this one. So this register gets a write enable, and then we can also turn the data input line on, which we can turn the data input line kind of the same thing with the write and read enable wire. It can go on for every register in the grid, but none of them will do anything because they're not actually receiving the write or read signals, like I said before. So this way we can have a network of wires going to every register in the grid, and we won't have to address each of them specifically. We can just turn on the whole network or turn off the whole network, and none of the registers, except for the one we specify, will actually do any work. That is very convenient, and it also even works for the data output too. We can just have one grid for data output that we say we read down here as a 8-bit output. We can just take that from all of these, because as we know, it'll only ever be coming from one of these registers. So here you have a complete diagram, and this is the same grid from before, but here you can see the vertical and horizontal wires are connected to these multiplexers. Multiplexers in a computer are what take binary inputs and turn it into a single output on one of these memory modules. So let's give the multiplexers a binary input, like 0, 1, and maybe this one go 1, 1. If you don't know how binary works, it's pretty simple. It's just each place to the left represents twice as much as the previous place, and it starting from ones, this is the ones place, twos place, and there's the fours place, eights place, and so on. But assuming you already know that, each of these multiplexers takes a 2-bit input, because that's 2 bits is all you need to distinguish between 4 different options. Now, bigger computers might have like 64-bit multiplexer inputs, which is absolutely insane for storing like gigabytes of memory. Here, we only have 16 bytes, so that's like billions of times less information density. But So as you can see, 0, 1, that would reference the first wire. So this one is 0, this is 1, 2, and 3. So first wire, that would be right here. So we turn this wire on. And then the second multiplexer, we have a 1 and a 1. That would be 3, so the last wire. No, we turn this one on. Sorry, that's just the border. So, as we can see, this is the register being turned on right now, because it's right at the intersection of 1 and 3. So the next thing we do is we'll have either the read or the write enable on. So let's just say we have the write enable wire on. That will send a signal to every one of these, but it will only activate on this one. And then we'll have the data in. We can just have random set of numbers right here. So if we turn on the write, send those numbers to the multiplexer, data in, all of this will end up writing this 0, 1, 0, 1, 1, 1, 0, 0 to this register. Now we can turn all of these off. Let's turn all these wires off, get rid of the inputs. And now this register still has that number stored even after we no longer feed into it. So then later, when you want to do a calculation with that, you'll send in the read signal, you want to have a data input because you're reading, and then you'll send the memory address, which you'll remember, well, the computer will remember as 0, 1, 1, and 1, and then it will request the information from this register, which will be then output over here, 0, 1, 0, 1, 1, 1, 0, 0. That's how RAM, or random access memory, works. Because as you can see, you can choose any of these blocks in the grid, and when it's a much larger grid with millions, even billions of these little registers, you're able to pick one out at random and read, write, reset, do all of that to it. And it's been a few hours. This is the final product. So this is the complete 4x4 grid registers. So in total there's 16. And each of them are hooked up just like they were on the diagram. These blue lines are the column wires, and then these red lines are the row wires. It doesn't matter if you call them column or row, they're just forming a grid. That's really all you need to know. That was a great rhyme. But they're each wired up in the same way. So at the intersections, there's an AND gate between the two wires, feeding into two other AND gates for the read and write signals. So we can specify which register we want to read to, or we can specify which register we want to write to. All of this yellow wiring you see here is just to carry all the different signals around. Like this yellow wiring is just the input wiring from the console over there. And then all of this wiring and this wiring going from there down and back over there, that is the output wiring that we'll see over here. This is our multiplexer, or the register selection, where we put in the binary address, and it selects the correct two wires to specify the one register we want to get through our binary address. Here, we can give it a test. So this book I have is, I've already preloaded some information into some of the registers, and we have the addresses right here and then the information over on the right that we should get if we read from it. So let's try 1100. We insert 1100 on the multiplexer, and then we go over, then flip the read signal. Great, we get 10101010. Is that what we should get? 1100. Great, 10101010, because that's what I loaded in before. Now we can load in a different value, say like, let's just make it all ones. Turn off the read signal. Turn on all the input wires. And then we have to write it to that register. Turn off all the wires. And now we should be able to read that back out. Great. 1111111111. Because there's 16 registers, there is space available for up to 16 different sets of information coming out of here. And this is pretty much the basis for computers, because you can't have a CPU that runs without actual memory to draw numbers from, because what's going to happen is later on when we get to building like actual CPUs incorporated in our ALU and stuff, is that there's going to be a smaller bit of memory in the CPU that will remember the addresses to input on the multiplexer. So it will send out a request into the RAM for a certain address, and then it will take the numbers that output from that, and it will be able to perform logic on those numbers, as well as be able to input the address and write a separate set of bits if it wants to save those. That is this overview complete. Thank you for watching.